One of the things that's very important to understand the different absorption spectroscopies, specifically ones that use electromagnetic radiation, is actually understanding the electromagnetic spectrum. Okay? Okay, who here is being irradiated right now? Yes, you are. We're all being irradiated right now, aren't we? What's the most powerful radiation source in the room? Can anybody tell me? Yes, the sun is the most powerful radiation source on the planet. And unless you get to very specific locations. But in the room, the most powerful radiation source is actually that right there. Okay? That projector. So that projector is irradiating me far more than even if I was standing next to a nuclear reactor getting the full brunt of that radiation there. Okay? Okay, that's the most powerful, intense radiation source in the room unless I turn the lights on. In which case, those lights, bulbs, all those would be much more powerful. Okay? And that's because the electromagnetic radiation is the primary and most common source of radiation you're going to see. Okay? Now, having said that, nuclear radiation is actually in your bodies. You're all nuclear radioactive. Does anybody know what happens if a nuclear plant has an emergency? A breach of any sort? So by federal law, any radiation source is considered a radioactive contaminant and needs to be disposed of. You are all radiation sources. So the actual law right now as written states that you should all be disposed of as radioactive waste because there is a zero limit. That means there is absolutely no limit to the radiation that needs to be disposed. So the sun needs to be disposed, you need to be disposed of, the light bulbs needs to be disposed of, the air needs to be disposed of. Yeah, it would be an interesting case because the federal government has very clearly stated zero limit.
It is radiated.
Yeah.
Job.
Radioactive material.
Yeah, exactly.
Yeah. You need to throw it in the bunker. Sometimes federal law is just so fucking stupid. Sorry for that. But anyways, so this right here, when we talk about very, very light things, they have what's called a wave-particle duality, okay? And I'm not going to get super far into this because this is more quantum, right? But know that spectroscopy ultimately is a quantum study, okay? Everything that spectroscopy does happens on the quantum levels, right? And you operate in quantum. Everything happens in quantum for you, okay? Your very thoughts are quantum effects, right? So when people throw quantum in front of something and make it sound fancy, it is not. Interesting little factoid. Did you guys know that Microsoft just completed a 28-year study where they made new quantum chips? Yeah, so it looks like quantum computing is... Anybody know what a CUDA core is? It's what your graphics card uses to render fancy stuff. Yeah. So you have a bunch of different types of cores in your computer, and very likely in the next 5-10 years, you're probably going to have a quantum core. Yeah. That will do nonlinear calculations for you. Yeah. And make those much faster. So really cool stuff. If you ever get interested, if you're interested in any of this sort of stuff, look up online. Very amazing. Yeah. Like a total paradigm shift. Right. Completely new materials, everything. Really wild. Okay, so when we're talking about very light things like photons have zero rest mass. They're about as light as you can get. They're going to have very, very large wave-like properties. Very little particle-like properties. As you get more mass, you get more particle-like. Okay? Okay. And so once we get past like a proton mass, that's what you're going to start having your normal model of the world working, okay? It's going to be basically completely particle-like. Everything that you've known about the world around you starts working again, okay? When we get down to the electrons, they're much more quantum-like, okay? Because they're very light. Now, what does this mean? This means they actually pop in and out of existence, okay? You actually have no specific location that they are in during certain times. Okay? And so you actually very much need to treat them as a probabilistic function, that they have a certain probability of showing up here. Okay? Remember our orbitals, we had 90% probability of finding the electron in this space. That's the sort of thing we're going to be talking about here. Okay? Okay, now, if we look at energy of a photon, photons are the individual quote-unquote particles of light. They're going to be the energy equals Planck's constant times the frequency of the photon. So energy is direct proportional frequency, isn't it? Okay. And then, if you substitute in the previous equation we had discussed, the energy would be inversely proportional to the wavelength. And that goes through Planck's constant times the speed of light over the wavelength gives you the energy of the photon. Should an individual photon be a lot of energy, by the way? No, they're going to be very small amounts of energy. Okay? If an individual photon was a lot of energy, then any light at all would just blast you into smithereens, right? So, obviously not happening. So, yeah. That light bulb would be a death beam, right? Okay. And there is actually really, like if we were fully exposed to the sun, this is one of the reasons you can't travel to Mars right now and expect to survive it. You would actually, yes, it would be a death beam to you. You would die. It would take like 10, 15 minutes if you're fully exposed. If you're in a spaceship, it would take like 3 months. Okay? But you would still die. So the energy given by a photon, again, directly proportional to the frequency. So when we talk about these energy values, keep that in mind. So right here we actually see the electromagnetic spectrum. And this one's an extremely abbreviated, kind of not really correct version that your organic textbook uses. You can very much tell this person is a very medically oriented organic chemist. Okay? All right, so on the bottom of the energy scale, the lowest energy, these are radio waves. The lowest energy of that is the AM. Anybody know the AM radio? Okay, you like look at the radio, there's the AM stations, right? Yeah, those are the lowest energy, longest wavelength ones. They have the furthest distance that they can go through objects because they have very long wavelengths. So the probability they actually impact and significantly interact with the particles in between actually goes down a lot. Okay? Notice that they have very long wavelengths. We're talking like kilometer wavelengths. Okay? Okay, so above that is going to be FM, then TV, then radar wavelengths. Now, keep in mind that this radio waves here should actually have a section that's called microwave radiation up here. That's why radar, for example, is a microwave dish, right? Anybody ever heard of that before? Yeah. And so what you're going to see is those are going to be wavelengths that is going to be in the micrometer scales. Okay. Anybody ever heard of 5G? What's 5G stand for? You guys are getting it. It's not bytes though, it's gigahertz. Yeah, because that's the frequency scale, right? So it's literally 5G is over here. It's just a little shy of the infrared, right on that line. And that's actually 5 gigahertz electromagnetic radiation. Okay? And you can change what's happening and pass the data faster using that. 4G was 4. 3 and 2G were kind of both 2 somethings. They were just slightly different technologies. But yeah, so like your Wi-Fi signal in your house, very likely you're using something in the 2 point something gigahertz range. Okay? And that's this microwave radiation. Anybody ever heard of a microwave that used to heat food? Mm-hmm. Okay, what does a microwave have in it? What does it do? Yes, so it releases, it's a very powerful source of electromagnetic radiation that's in the microwave region. Okay? And it does a very specific frequency that corresponds to water molecules. Now, in that region that it does, what it causes is the water molecules to spin. Okay? It's still in this region, actually, right here. And what happens is when the water molecules are spinning, they start hitting each other and causing them to bounce around. And randomized kinetic energy is heat, isn't it? And so what happens is when you microwave something is you literally cause the water molecules to start spinning around, knock each other around. That creates heat, and that heats the object. What happens if you don't have water, by the way? Doesn't get hot, does it? Yeah, anybody ever like done a burrito? It didn't heat at all in the middle? Yeah, really cold? Yeah. Or it didn't heat on the edges if it's has a lot of water in it. And so what you're experiencing again is the water is where it heats, right? Because it absorbs in the water. The outer part, like if you had a lot of oils in the burrito, that burrito's not going to heat where the oils are, right? Yeah. Okay. Anybody know what Einstein is actually famous for?
E = mc².
That's what he's famous for, but what made his career? Okay, so Einstein was actually a good scientist, but mostly a theoretician. But he was a great theoretician. And so he predicted that electromagnetic radiation could cause metals to start ejecting electrons. Anybody stuck a fork in a microwave or tin foil? That's what he predicted. Okay? And so once we started getting microwave sources that are fairly powerful, that was actually confirmed. And what that is it's the ionization energy, isn't it? So when you put microwave onto a metal object, the ionization energy is fairly low for metal objects as compared to nonmetals, right? And so what you end up doing is you actually eject electrons from the metals. Ejected electrons in enough amounts is electricity. Okay? And that's what electricity is. It's moving electrons, right? So anyways, now we've done a little bit of microwaves. Again, these cause down here things to translate and rotate. Okay? So they cause nonmetals to translate or rotate, i.e. vibrate a little, like a radio vibrates quartz sort of thing, or they cause them to rotate. Okay. This right here is the infrared portion. This is what we're going to be talking about a lot this chapter. Okay? And this portion right here causes molecules that are nonmetals to vibrate, like little springs. Anybody ever played with the little spring or a slinky? And it goes dink, dink, dink like that? That's a vibration. Okay? That's what's going to be caused every time you put infrared radiation onto a nonmetal. If you think about metals, metals just move down the spectrum. Okay? So, for example, like a metal, you're going to be ejecting electrons from that again. Okay? Okay, and so this is the infrared spectrum. Over here is what is called the visible light spectrum. It is a total bullshit designation. Anybody tell me why we bother designating that separately? Because the majority of humans can see in that region. See that little tiny sliver? That's it. Okay. By the way, is that true for all humans? No. There's hypo and hyperchromism. Okay. Men tend to have hypochromism, meaning they can't see all the colors and they can't see all the frequencies. Women tend to have hyperchromism, and 1 in 10,000 women can actually see in the ultraviolet and near infrared. And so they have extra colors they can see. That's some superhuman stuff. By the way, like shrimp and some different organisms can actually see way into the ultraviolet and all the way down into microwave. So there's some pretty crazy stuff out there. Okay, so the visible light ultimately really should have had, this is red right here, infrared is below red, see that? And to be honest with you, red is actually more like infrared than it is anything else. Okay. Once you get past red, you start getting into what should have been like the super low energy UV. Okay. Okay, so what happens when you expose things to visible light is nonmetals actually have electrons that boost up into those higher energy orbitals. Remember where we had like orbitals? And we went, carbon, for example, had a 2p orbital, right? Everybody good with that? Remember that? Okay, but it also had space where it would have had a 3s orbital, right? Like the space exists, it just doesn't get filled because it's high energy, right? When you expose things to visible light, what happens is the electrons boost up into those orbitals. Okay? When you energize something, like give energy to a light bulb, and then it radiates light that's in the visible spectrum, what's happening is you've boosted something up into one of these higher energy orbitals, and then it falls down, and it releases energy. Okay? Everybody good with that so far? Okay. All right, so what's going to happen next here is we're going to get into the ultraviolet. That's the UV, ultra meaning higher than violet, right? The highest energy portion of the visible light is violet, isn't it? Okay. Okay, and so ultraviolet, everybody's heard of that before, right? UV radiation gives me sunburn, right? Okay. Okay. There's actually 3 important regions to this in terms of biology. Okay? There is the low energy, mid energy, and high energy. Usually referred to as low frequency, mid frequency, high frequency. Anybody remember where we always were having H and then a little V symbol next to reactions? We had a lot of reactions where that was a condition. That's high frequency light. Okay, that's high frequency, somewhere in the mid to high frequency UV usually that you use. And so that little flashlight I had you all use, that was again a low wavelength or high frequency UV. And that's why I was telling you guys, don't look at it directly, don't don't flash each other. Okay? Okay. Because does anybody know what happens if you use high frequency ultraviolet on a person?
They go blind.
They go blind because it damages their cornea. In fact, that's usually why you end up with clouded cornea later on in your life. Is a lot of exposure to the mid-frequency or high-frequency UV over time. Okay. The other thing that happens here is about 10 to 15 minutes of exposure kills almost every organism on the planet. Okay. Did you guys know that we almost wiped off all life on the surface of the planet? I told you that, right?
Yeah.
Okay. Why was that?
Ozone.
Yeah, we almost wiped out the ozone layer. And so it only taken about 10 to 15 minutes of exposure to the high frequency UV that hits the planet all the time to kill everything on the planet. So, unless it was, of course, protected from that light. UV absorbs really well by glass, by the way. That's why most of you don't tan when you're near a window. Okay? Especially if you're like a double or triple pane window. You're not going to tan. All right? So it absorbs really well with the glass. So you get protected by glass fairly easy. X-rays, everybody has had or seen an X-ray, right? Medical. Okay, that's just very high frequency electromagnetic radiation. You don't typically see this except for like nuclear. So a nuclear source of some sort, or you can actually take... Anybody ever seen the old boob tubes? The old vacuum tube? Like TVs and stuff? Okay. Did you guys know that if you took those old vacuum tubes and hooked them up to a high enough voltage, you actually emit X-rays? Yeah. It's one of the reasons they went away and you don't see them sold or like released anywhere anymore. Because if you hook them up to the wrong voltage, you'll actually make an X-ray. Yeah. Anyways, gamma rays, no, they don't turn you into the Hulk. They're just very, very high energy electromagnetic radiation, right? Okay. And so gamma rays are very unusual to see except for radioactive elements. Okay. Radioactive breakdown or fusion produces gamma rays pretty commonly. Okay. Anybody have any questions on this stuff? Right. So I told you that visible light boosts things up into higher orbitals. Once you get to the high energy ultraviolet and X-rays, what they do is they just smash the electron completely out of the orbitals. Okay? So it's like a rocket, just leaves the entire atom. Okay? And then if you do that to molecules, what happens to anything next to those molecules? You're going to have the bonds start breaking. You're going to smash apart the bonds, right? You do that inside a human or on their skin, guess what happens? Yeah. You're going to get things that are very, very important, mostly RNA, actually. Did you guys know that your process of like sunburns is usually actually RNA? Yeah. But also DNA could end up getting reacted. If you have reactions on your DNA and RNA, they're going to block protein synthesis, and you're going to have adverse reactions, right? DNA may cause mutation, and then you could get cancer. Okay. So let's talk about infrared spectroscopy. So infrared spectroscopy looks a little complicated right here. But ultimately what it is infrared spectroscopy is you just throwing light that's in the infrared region through a sample and then collecting what light comes back out. Okay? So it's the same thing you do with your eyes. Technically you're using visible light spectroscopy every moment that you're looking at me. Okay? That's how you're detecting where I am, what I'm doing. Yeah. All the colors if you have color vision. Okay. So this right here is an infrared instrument, and so what you see is it has an infrared laser usually. Actually, you don't actually use an IR laser in almost any infrared instrument that I've ever seen and heard of in my life. Your book, again, is very weird. It's obviously this person is not a spectroscopist, but this right here, what you typically use is you use an infrared source. It's called a glow coil. It looks like the coil you would see in an oven. Okay? And it has a laser that's also attached to it. And that one is a red light laser. It's not infrared at all. Okay? So what's going to happen is you're going to take that light, you're going to go ahead and put it through a splitter of some sort, and you use the splitter so you can go ahead and take off the amount and the portion you want to actually look at. Okay? So you just split off what you want to use. This is ultimately going to do some transformation, but that doesn't really matter that much to you all. What's going to end up happening, though, is you are going to put this through a sample. This sample can be prepared in a large variety of ways. This could be a gas, it could be a liquid, it could be a solution, it could be a solid powder, it could be a solid pellet. Doesn't really matter to you, I imagine. Okay? But you put it through a sample of some sort. Most of you, if you ever go into industry or do this as a lab tech or something, this would end up being probably an ATR, called an attenuated total reflectance. Okay? And what that means is that you don't actually pass through sample, you bounce off the sample. Right? That's the big difference there. All right. So once that hits the sample, what happens when light hits a sample? Does all the light come back? Mm-mm. And if I put some red gauze over the window, what color would come? Red, right? Why does red come out?
Because all the other light is absorbed.
Yes, exactly. The other light is absorbed. Specifically, the opposite color is the one that's most absorbed usually. Okay? And that's what makes thing a certain color, right? Same thing's happening here. It's just these don't have colors because we can't see them, right? And so specific frequencies are going to be absorbed based on what that material absorbs. It absorbs things based on it matching the frequency it vibrates. Okay? Anybody ever played with a bell set when they were a kid? Or a chime set? Okay? Anybody ever got one that's a dead bell?
What?
No? Okay, do you guys know what a dead bell is? Okay, so what bells are, or chimes are, or xylophones, or any of these things, is the mechanical impact causes it to vibrate at a certain frequency. That vibration, that frequency, is the sound note you hear. Okay? All the other frequencies get killed off by it. They can't resonate with it. And so those are called dead regions. Now, if you take those and you damage them in the exact right way, you'll actually create what's called a dead bell. Okay? And it's where you hit it and you can't actually hear anything because you've destroyed the resonance completely. So like this, you can hear stuff. A dead bell actually negates all the frequencies you can hear. That none of those can resonate. Yeah. It's kind of a neat phenomenon. Anyways, so that's actually what's happening here. You're essentially hitting your molecule like you would a xylophone, and then you're looking for the frequencies at which it's absorbing instead of the ones that come back off. Okay? Okay, did that make sense for everybody? Okay? Okay. And so what we're going to have here is a detector. What you actually are doing here is you're hitting it with a specific frequency. So you hit it with one frequency after another along this spectrum here. And that's what you're seeing over here. And then you see how well it absorbs each of those. Okay? It'd be kind of like looking for something by going across and just tapping it. All right. So this is actually what an infrared spectrum looks like. This is in percent transmittance. This is the better way to look at the spectra, but you very likely have only seen spectra in absorbance. Is that correct? When you used your UV vis instruments? Okay. Yeah. Most non-spectroscopist instruments default to absorbance. We'll talk a bit about absorbance, but know that transmittance is the literal intensity of the light that comes through. So it is the intensity that comes to the detector divided by the intensity from the source. This is actually why you need to split the light. So you can measure the intensity it comes off at versus the intensity it goes through your sample. Okay? So, and then it's a percent, so times 100% to make it a percentage, right? Okay. And so it's literally the percentage of the light from your source that came through your sample. All right. So this is your percent transmittance here. And so what we look at here is about 100% should be what's called your background is. Okay? This is your background right here. It's the I'm passing through the air, so some of me gets absorbed. Okay? And that's your background right here. See that sort of flattish surface right there? By the way, this is actually not a good infrared spectra either. Which is, it's funny because I just took these from your book because I was like, okay, they're the ones from your book. You guys will be familiar with them. But see how this is like this? Everybody sees that? Okay, that's how you know it's a shitty infrared spectra. That whoever took this didn't really know what they were doing. Okay? And the reason for that is the background, i.e. everything else in the world, except for the sample you want to look at, everything that happens when you pass through the air, the moisture in the air, the CO2 in the air, etc., and your windows. See how this is between two windows? Okay. That window has this shape. So if you do a bad background where it doesn't actually match up well with your sample you're taking, you get this shape. That tells you it's a bad background, that you've done a bad job on your spectra. Okay? These peaks right here, these negative ones, are actually CO2. So we're actually seeing the CO2 in the lab right there. Yeah. This is water right here if you're curious. And see how they're negative peaks? So when they first did their background, the water and the CO2 was actually more than what they had when they actually did their spectra. And again, them being that tall is actually a sign that they didn't really know what they were doing. Yeah, they didn't do a very good job. Anyways. So these are what are called absorption peaks or absorption bands. Okay? And they are where your sample is absorbing the infrared radiation. So see how they correspond to these wave numbers here? Wave numbers are actually a 1 over wavelength scale, the wavelength being in centimeters. Okay? They're the most commonly used for infrared spectroscopy. Very, very rare to see any other scale used, but you can do this in frequencies, you can do this in wavelengths. These are all interchangeable things. Okay? You can actually just set the instrument, tell you which one you want. It's like the secret sauce to know if somebody knew anything about infrared spectroscopy, to look down here. If it says wavelength, if it says something in nanometers, then they didn't know anything about infrared spectroscopy at all. If it says down here a frequency, you also know they didn't know anything about infrared spectroscopy. They're totally ignorant, no idea what's going on. Okay. This person knew enough to put it that, so they've used it before. So we're doing good. Okay. Anyways, you see that you have a variety of absorption peaks. These things can get fairly complex, but there's actually a very, I'll teach you more about it on how to assign these in a bit. Okay. But this right here is called the fingerprint region. This right here tends to tell you very distinct functional groups. Okay. This one right here is actually carbon hydrogens. And see how it's real broad? Okay. That's actually because there's a bunch of carbon hydrogens. Right. Okay, see the broadness of these peaks? How broad should a peak actually be? How about that one? That's pretty sharp, isn't it? Sharper. That one's a bit sharper. So actually, if these peaks had nothing else going on than the vibrations, they would be single lines coming down. That's it. They'd be completely sharp. Anybody ever used your camera and you didn't have the right zoom on? Okay. What happens to like a pencil when you have the wrong zoom on? It's blurry and it's wider, right? Yeah. And so what's happening here is we're actually having broadness because our resolution is not as high as it needs to be to see the individual objects. Okay? And that's why you're seeing this broadness that peaks. Otherwise, they'd be a bunch of lines that would be the same shape. That making sense? Okay. And what you're actually seeing here is as you increase temperature, you get a lot more bouncing around, deformations, the molecule deforms a bit, right? Because it hits each other. You also get things like rotations. And so that's the things you're seeing. If you were to reduce the temperature for this to like negative 200 degrees Celsius, you'd see almost all the width here drop off. They'd be real sharp. You wouldn't see all the width drop off, but pretty close. Okay? That's actually part of what makes these broader. If you do spectra like in the gas phase, you're going to see they're much broader than if you did it like in a solid. Okay? Okay. And that's actually why if you take solid phase, like NIST, does anybody know what NIST stands for? National Institute of Technology. It's who sets most of the standards for like the industry and stuff. They actually recommend you only do a 4 wave number, that's the wave number, resolution. Like a camera resolution of 4 out of this. Okay? For a solid or liquid. Okay, so let's go ahead and go on to the next part. So these ones right here are what's called strong absorption. That means the percent transmittance is very close to 0. Weak absorptions are going to be ones that are up here. So this is very weak absorbers right there. This one especially. See that little peak? Okay. And they're very close to 100%, right? So most of the light went through, they barely absorbed. Okay? You, of course, can subdivide that into mid, etc., as much subdivision as you want to do. Okay? One of the things I need to warn you about, though, is You typically do not want to go much below 20% for your strong absorbers. Anybody know why you would not want to go below 0%? What happens if you hit 0%? Yeah. So if I were to turn off all the lights in my mid room here and put you in there, would it be dark? Yes. Would you be able to see anything? No. Is it absolutely no light whatsoever? No. You just can't tell anymore because you can't see anything, right? And so if you get dark enough, i.e. 0%, you can't actually tell any further down than that, right? And so you'll actually blow your peaks through the bottom. Okay? And you just can't measure it anymore. Right? There is cases you might need to do that. For example, if you're trying to look at this peak right here, and that's really important, you can blow the rest of the peaks down through the bottom and just see that. Okay? But in general, watch out. Okay, so this right here is your general theory for your different motions. These are called vibrations. They're like springs, okay? So this would be the spring where you take it and stretch it and then release it. What happens? Dun, 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 right? Okay. And that's called a stretch. This right here is another stretch. You're just having symmetric. It's like two hydrogens going like this. Okay? So you have two hydrogens stretching on both sides. This is an anti-symmetric stretch. It's where one is stretching out of frequency with the other. See that? They're opposites. Anti-symmetric. This right here is called a bend, and what you're seeing here is this is where it's deforming. So you took your string and you went doing. Okay? And it's on the side, right? Making sense to everybody? Okay, this is right here another bend. I'm not going to go super far into all the bends. There are plenty of bends, and your book I don't think really encapsulates all of them, or even does a good job using the terminology. But you guys, unless you're going to go super far into infrared, take instrumental with me. We can go into what the different types of bends are and stuff, okay? Otherwise, you guys are probably not going to need that. Okay. All right, so this right here is going to be the absorption of an infrared photon. So what you have is an infrared source coming in. So an infrared photon hits your molecule. That happens to be the correct frequency to boost it to a higher energy level. And so what you would see is normally like a spring that has a little energy in it, and most of these molecules are sort of stretching out and doing their different vibrations just a little. Okay? So real slow, real not a lot, right? And so this is what's called ground state. We hit it with an energy source, so a photon hits it. It's the correct frequency to boost it up to another energy level, which is a higher frequency. You can think of it as the octaves. Okay? Did you guys know octaves are repeat of the same frequency patterns? Yeah. So when you go up an octave, you actually get the same frequency pattern times 2. And that's what the octaves are. Okay. You knew that? Cool. Yeah. That's exactly right. Yeah. It's funny because most people don't really know that. It's kind of a cool fact. Okay. So anyways, so here we see the infrared. Notice we could have boosted up to higher energy levels. That's going to give us more drastic frequency, higher frequency vibrations, right? Okay, so this one right here has a vibrational frequency that corresponds to 2,961 centimeters -1. Okay, reciprocal centimeters. This one here would have a vibrational frequency. It's going to correspond to 1717 wave numbers. this is, anyways, I'm going to let that statement right there from your book stand. And I'm going to just sort of walk around it, okay? That's a good enough idea for you guys. But anybody that wants to go further infrared, this is not true. That's just not true at all. Okay? It's a nice model in your head for when you're first learning it, but the frequency of these vibrations is not the frequency of that molecule. That's just not true. Okay? That doesn't make any sense at all because you can have different masses. Like, wow. That'd be like saying high tension spring has the exact same frequency as like a low tension spring. Or like the heavy block on the xylophone has the same frequency as the small block. The light blocks. Like, wow. Okay. So let's talk about the locations. The locations are the most important thing. They're what you really need to understand when you understand infrared spectroscopy. If you're going to learn anything from this, learn that the locations of these peaks in the infrared spectroscopy, those are heavily going to correspond to the functional group. Okay? Just so funny. They actually disprove their own statement within the next section. I forgot of that. That was a thing. Yeah. Okay. So, again, for example, right here we have a carbonyl. And so a carbonyl is going to have a stretching frequency that's going to be about 1715-ish. Okay? This specific one is 1717. And so there's a table in your book, and that's a good place to go ahead and use when you're doing your homeworks and get used to using that information where each of the functional groups is going to have a peak up in this region right here that corresponds to it. Okay? This region down here, see how that's complex? So remember how we took our GCMSs and we worked from low complexity to high complexity, right? You want to do the same thing here. So what you want to do is get what you can out of the low complexity region. Okay? And then if you need it, you can go to the high complexity region to get more information. But it's going to be more difficult, right? And you're going to have less assurity. Okay? Okay, so again, we see another carbonyl. See how it's at the end there? It's that nice aldehyde. And we see that that one has a 1723 wave number stretch. So you can actually tell a little bit of difference on these functional groups, like what's attached to them. But the big thing I want you to focus on for now is the functional groups and that location of the peaks. Okay? Okay. Now, there also is going to be the band strength. That's going to show up in these tables as well. Always use the frequency first. Frequency is by far and away the most important consideration. The frequency doesn't match, I don't care how strong the band is. Okay? If the frequency is 3000, it is not a carbonyl. I just don't care what the band strength is. Okay? Doesn't matter. Right? All right. If there's your face up in the sky there, a kilometer above the ground with nothing supporting it, that's not you, is it? If it is, I don't have to worry about it in a little bit. Okay. So, frequency first, and then you can use, if there's two bands it could be that are fairly close together, you can use the strength of the band. Okay? So, for example, the alcohols tend to have a bit of overlap with things like the amines. See that? They tend to overlap. But the alcohols are broad and strong, so they're very broad bands. They're very strong. Okay? The amines, on the other hand, are medium bands that have a sharp low point. Right? And so they look very different, despite the fact that they share the same sort of region. Okay? Okay. Mm-hmm.
When it's saying strong, that's like referring to how deep it,
Yep.
like how close it gets to zero.
Got it. Yeah. So this would be strong narrow bands. There's just a lot of them because it's carbon hydrogens. This right here would be a weak or medium, depends on the spectrum, but probably a weak. And that's a sharp band right there. Okay. Strong narrow band again. Okay. And when we get into alcohol, you'll see the broad bands. But they're like this. They're broad. You'll be able to get it. Okay. Any other questions here? Okay. Now this table right here, I'm going to be honest. I personally don't see a huge amount of value in you memorizing this table. However, the ACS exams especially really like asking questions about infrared spectroscopy and then not giving you this table with the functional groups. So it's a pretty popular question for MCAT. It's a pretty popular question for a lot of testing. Okay, if you go to grad school, you probably are going to take a test that's going to ask something about infrared spectroscopy, and they're very likely not going to give you this table. Okay, so I personally am going to allow you to use notes, right? And so technically you can have that table on your notes, but considering that the the exam at the end, ACS, is going to replace an exam, so you might want to study and have some idea of how to do well on it. You may actually want to semi-memorize this table, okay? And if you go on and do any testing with organic chemistry on it, I highly recommend you have a decent idea of the table, okay? Don't spend all your time on it, but have something in your head, right? Okay, so again, these are your amines, your amides. This is alkyne, alkene, and alkynes. Notice you can actually tell the difference between the 3 single, double, and triple bonds fairly easily with infrared spectroscopy. This is aldehydes. And right here you have a variety of the other groups, including the aromatics. Okay? These ones right here are all the portions that are above the fingerprint region for the most part, except for down here where we start getting into the fingerprint region and you'll start getting more complexity. Okay? Typically the fingerprint region though is considered to be 1450 and below. Okay. And it looks like a fingerprint. Yeah. Now, most organic books are going to essentially state that the use of infrared spectroscopy is to find what functional groups are present and then to find if you have one enantiomer versus the other. Okay? To determine what chirality you have. You can also do that. That is very entry level. That's like saying you can only use a screwdriver for turning screws. Anybody that's actually used a screwdriver knows that's not true, right? There's a lot of uses for a screwdriver. There's a lot of uses for infrared. That's well beyond just identifying functional groups, okay? But I don't have time to go through all that. So your level of use for infrared is probably just going to be contained to mostly identifying functional groups. That's going to be your major thing, okay? Okay, so let's go ahead and use that table. We're going to take this question right here and figure out what frequencies of IR absorbed peaks would appear for each of these stretching vibrations that are indicated here. Note the bends typically show up in the fingerprint region, that lower frequency region. Okay, so it's usually the stretches we're going to be looking at. We'll mostly end up ignoring the bends. For all of you, the fingerprint region, you're going to literally use it like a fingerprinting a person. Okay, so you're going to take a known sample, take an infrared spectra of it, line it up against an unknown one, and see if the fingerprint matches. Okay? The higher frequency region is the one you're going to use to figure out what the heck it could be, if you don't know what it is already. Note that if you're trying to identify a substance, never, ever, ever, ever use a single spectroscopy method. Okay? You will almost certainly end up getting it wrong, and then you'll lose the company billions of dollars possibly, or give people the wrong drug and kill them, you know, variety of things. So if you don't know what it is at all, use at least 2. Likely you're going to need to use 3 techniques. Okay. Anybody knows I'm teaching you 3 techniques? They're the 3 most common techniques that are used to identify compounds. I know. You can use these 3 together. NMRs are a little expensive though. So you may have to use more non-spectroscopic techniques to deal with it. Okay. All right, folks. Everybody got your table and looked up your values? So what's the values? What's the values? Okay, so if we have a carbon-hydrogen stretch, we're going to have an alkene, right? We have a carbon-carbon double bond. The region that would show up in is 1620 to 1680 wave numbers. Mm-hmm.
Why is that not 3000 3100?
This is carbon-carbon. So, for example, this right here is the carbon-hydrogen, or right here, carbon-hydrogen. The carbon-carbon would be down here, right here. Yeah. So this would be taking that bond, the carbon-carbon bond, and stretching it. This one would be taking the carbon-hydrogen next to it and stretching it. Okay. And yeah, the carbon-hydrogen stretching is going to be this one here, okay, which is B. Okay, so B is going to be an alkene carbon-hydrogen, and that's going to be 3000 to 3100 wave numbers. The next one, which is C, is going to be an ester. That's going to be a carbon-oxygen here off of an ester. And so that's going to be 1730 to 1750. If you got more into infrared spectroscopy, you can actually tell esters from other carbonyls fairly easy. But I'm going to leave that for here for now, because we won't get too far ahead of ourselves. The carbon-oxygen single bond is going to be 1050 to 1150 wave numbers. Notice that as you get a double bond, what happens to the frequency? Increases, yeah. Yeah, vibrates at a higher frequency, doesn't it? Okay. If you make a stiffer bell or you make a stiffer spring, what happens to the frequency? Vibrates at a higher frequency, doesn't it? If you do a real soft one, like a slinky, vibrates at a real low frequency, doesn't it? Yeah. Mm-hmm.
So it's vibrating more because it's more stiff?
Yes.
Okay.
It's higher frequency vibration because it's more stiff, yeah. So double bonds always vibrate at higher frequencies than a single bond. Overall, shorter bonds vibrate at higher frequencies. Okay. If you have a lot of very low weight on one end, then it vibrates real fast, right? And so you get very high frequency. That's why like carbon-hydrogen bonds vibrate at high frequencies. Hydrogens are very light, so they can really go. Okay, and so everybody good with that? Alkane, carbon, hydrogen, 2,800 to 3,000.
For B, go back.
Mhm.
So it's asking for the that bond between the hydrogen and the carbon.
Yes.
So we would go based off of if there's an alkene next to it.
Yes. What's attached next to it?
Okay.
Yeah, those are going to change exactly the length of that bond
Okay.
and the forces that are holding that carbon hydrogen together. And so that ends up changing the frequency.
So if there was no alkene next to it, it'd be alkane.
It would be the alkane. Yeah, right up here. Okay. It's alkene, so it's that one. Alkyne would be up here. Mhm. Okay. And that's that S character, by the way. Remember how we did the different S characters? This one specifically is the acidic one, right? Yeah. Yeah, that's that same trend. Yeah. This is one of the ways they demonstrated that, actually. So, okay, so this right here is your major regions of the infrared spectra. Again, here we have hydrogen stretches. These are almost all hydrogen stretches of some sort. Okay. This right here is going to be mostly the triple bond stretching. This here tends to be the double bond stretching. And then down here, 15 to 1,000, 1,500 to 1,000, tends to be the single bond stretching. And then here, what's usually considered the fingerprint region, this is going to be your bending modes. Now, note that these two regions start merging right around here. So there's a bit of gray area right there. Okay? Okay. So one of the things I need to mention is you've noticed there's all these little tiny bands here that don't really correspond to anything in these molecules. Okay. There's something called overtone and combination bands. Okay. And so, has anybody ever like double tapped on a spring and gotten the perfect timing on it? No? Or double dribbled and got the perfect timing on it? So like you do one dribble and then you wait for it to just start going down and then you accelerate it and you get another and it goes whoosh, right? Okay. And so what you're seeing there is you're seeing a combination of two vibrations or an overtone where we're doubling up that frequency. Okay? And that's these little tiny bands that are sort of, what the hell was that? And for the most part, you all can ignore those and they're not going to be an issue because you're not going to do complete vibrational assignments. Okay, where you assign everything. All right? But that's what that is. Mm-hmm.
So I'm sorry, like if it's more stiff and has more vibrations, why is like the triple and double bond have a lower transmittance than the single bond?
Transmittance has nothing to do with where it shows up.
Oh.
Yeah. Transmittance is how well it absorbs that light, not what frequency it absorbs. Right? So it has to do with how well it's going to actually capture those photons and your sample amount. Okay. Anybody remember Beer's law? No? Okay, so absorbance equals path length. Here, let me go ahead and write it out. Since you all said you didn't know. Okay, so absorbance equals the path length times the concentration times epsilon, which is called the absorptivity. Okay, so this is how well something absorbs equals how thick it is, right? So for example, the wall really absorbs super well, not because its absorptivity is necessarily amazing, but because it's thick, right? Okay. Concentration, so if you put a drop of dye, it doesn't absorb that well. If you put 2 drops, better. If you put more drops, even better, right? By the way, that's the CO2 in the atmosphere causing the global warming stuff. That's C. Okay? Absorptivity then is going to be how well it absorbs that particular frequency. So you can actually see that in your clothing. So notice, for example, several of you have different, same red, but some of them are darker than others, right? So like you have like a maroon looking, which is real dark red, right? And then slightly lighter maroon. See that? And then we have even lighter red. Can you show your shirt? There you go. Thank you. Or your bottle, I guess. So we have the different coloring depending on how well they're absorbing, right? Even though they're absorbing the same sort of frequencies. Okay. Okay, that making sense for everybody? All right, we'll move on to the next slide and we'll go ahead and go. You have a wonderful day, wonderful week, wonderful break. Okay. All right. Let me know if I forgot to change dates on something or some suchness. You guys always know that, right? Yeah. Okay. And have a wonderful break. Oh, let me ask you guys a question real quick. For everybody in the lab, the Friday lab, who here